All right, so let's continue now. So this is kind of an aside from all of this discussion to talk more generally about these ideas of positive geometries. Sorry, and stringy canonical forms. The stringy is in brackets, so there's a more general notion of canonical form, and there's a way of getting them in a way that's will make the language obvious. All right, so what is a positive geometry? Well, we've seen already, examples of these interesting shapes: pentagons, icosahedra, so on. So this is going to be everywhere in this subject. So a positive geometry, I'm going to just give informal definitions here. It's possible to say this all precisely. Well, at zeroth order, it's any kind of region which has a closed or compact region like this, but where it has boundaries of all codimension. So, in other words, this is a two-dimensional positive geometry. It has an interior that's two-dimensional. It has boundaries that are one-dimensional, like this, and it has boundaries that are zero-dimensional, like that. So this is an example of a positive geometry, whereas like a circle is not. Okay, a circle, this is not, at least. It doesn't have boundaries of all codimension, right? It only has a one-dimensional boundary. It has no analog of the vertices. Okay, but actually we want more. We also want that there is a unique differential form omega that has so-called logarithmic singularities, and we'll see what this all means in a second, on and only on the boundaries. So tied to the positive geometry, there's a form, as the positive geometry is P, there's a form omega of P, such that there's a differential form that has logarithmic singularities on and only on the boundaries of P. Now, the simplest example of positive geometries where we understand the most about them are when positive geometries are just polytopes, like triangles, polygons, cubes, higher dimensional versions of polygons that are called polytopes. Here we understand a lot about them, about polytopes. The polytopes are positive geometries, and we understand a lot about the canonical form for these polytopes. There are generalizations of the positive geometries that are like generalizations of polytopes. For example, there are generalizations of polytopes into Grassmannians, and that's the story related to the story of amphipohedra. But I'm not going to say anything about that. So we're going to stick with the absolute simplest positive geometries where we understand a lot about them in the case of polytopes, and I'm going to tell you there's still new things that we're learning about them, and the story of the stringy canonical forms is one of them. All right, so in other words, the positive geometries that we're thinking of are now really just like simple shapes like polygons or cubes and so on. Okay, so in all these cases, we have some geometric space that has boundaries of all codimension, and we're going to learn how to associate a differential form canonically to go along with these shapes. Now, why is this important as far as the amplitudes are concerned? Because what's going to happen is that in kinematical space, we're going to find some natural questions to ask. Okay, these natural questions will bring to light some positive geometries in kinematical space. not in some abstract, faraway space, directly in the kinematical space. In the story of the amplitahedron, this positive geometry shows up directly in the space of the momentum twister. In the story we're talking about here, it will show up directly in this Xij space. So the first thing that's going to happen is that in the kinematical space, we're going to discover these interesting geometric regions with boundaries of all codimensions. The way we're going to extract physics from that, the way we're going to get an amplitude or an integrand for an amplitude at loop level out of that, is that there's this differential form, omega, that is the slave to the geometry. So we want to figure out how to determine the slave to the geometry being given the polytope itself, right? And I'm going to now show you some examples of how this works. And then I'll talk about stringy canonical forms that are a sort of a new way. For polytopes, we have a number of nice, very intrinsic, invariant, beautiful definitions of what these forms are. And stringy canonical forms are a new one, and I want to spend a little bit of time telling you about them because they have a number of interesting applications. And they also unify a number of sort of threads of research in this subject over the past 5, 10 years or so. Okay, so let's start. Let's just jump into some simple examples. So let's begin. In the simplest case of a positive geometry is an interval. Okay, so let's say this is X space. So here's X equals A, X equals B, and the positive geometry A1 is just the kind of interior of this interval. Okay, so pretty boring. Now, but what is the canonical form? What is the canonical form of singularities on the boundary of this space? Well, obviously, if it's going to have singularities, let's just first remember something very basic about complex analysis. Let's say you have a singular, let's say you have a form that looks like dz. Okay, well, dz looks like it doesn't have any singularities at all. True. Let's say you have another form. It looks like dz over z squared. Well, that looks like it has a pole of z equals 0, but we know that that's fake because I can just write z equals minus 1 over w, and then this is just dw again. All right, so the only singularities that are really essential that you can't get rid of, and you can't get rid of them because attempting to integrate to find the primitive associated with the form would give you something with a branch cut, is dz over z. Okay, so it's these simple poles. This is the logarithmic singularity. That's really a singularity. And so we can write it as d log z. But of course, the log isn't well defined. Okay, so this is what's so that's the sense in which this is the most invariant kind of singularity we could be talking about. Okay, so if we want to have a form that has logarithmic singularities, so if we wanted to have logarithmic singularities at x equals a and x equals b, what could the form be? Well, obviously, it should be something like dx over x minus a, and then also there should be some dx over x minus b. And now again, we have this question, what should the sign be? Okay, and the answer is it should be a minus sign. Why should it be a minus sign? Because if it was a plus sign, then the form would have singularities. It would have singularities at x equals a and x equals b, but it would also have singularity at x equals infinity. Okay, so in other words, we know that the sum of the, by Cauchy's theorem, we know that the sum of the residues, has got to equal 0. Well, here we have a residue plus 1 at x equals a, and plus 1 at x equals b. So in fact, there's a residue minus 2 at x equals infinity. And of course, we also just see it from the form, because as x goes to infinity, this looks like 2 dx over x. So it also has a logarithmic singularity at infinity. Okay, so this is already slightly interesting. That in order to find, so here we have our first example, and the sign was fixed. And notice that the overall sign is not fixed. So this form has an orientation, just like if you like, the space itself has an orientation, the form has an orientation itself. So the overall sign is not fixed. Okay, so that's our first example of a positive geometry. what's our next example? Let's imagine we have a triangle. Okay, so here is x. This is x equals 0. This is y equals 0, and xy space. So this is my positive geometry, and this is, let's say, 1 minus x minus y equals 0. Okay, so now what should the form be? Okay, now, well, it's clear this is now going to be a 2 form, dx dy, over, it should have a singularity when x goes to 0, y goes to 0, and 1 minus x minus y goes to 0. So it should look like this. And are we done now? Well, no, we're not done. You see, we have to check something. This has the property that as, let's say, x goes to 0, I can take a residue of the form as x goes to 0. Now, we could define this formally by really imagining you're doing a little contour integral around x equals 0 and so on. But it's totally obvious in these simple examples what we're doing in practice. This is a 2 form. Yes. Was there a question? Yeah, sorry. The question is, we'll see how these forms are related to the ones that we're talking about earlier. Okay, the ones we were talking about earlier are going to be a special case of this general idea. Okay, so how do I take a residue of this form? Well, it's obvious. I go from a 2 form to a 1 form. So for example, the residue of this form as x goes to 0 is just what I get. I get rid of dx over x, and I'm left with dy over y, 1 minus y. Because remember, x goes to 0 here, right? So I sent x to 0. Okay, so let me go back to the picture then. So here I have this form. I have this space. This is x equals 0, y equals 0, 1 minus x minus y equals 0 on these lines. But if I take the residue of the form, the residue as x goes to 0, I get dy over, oh, sorry, this is x equals 0, y equals 0. So if I take the residue as x goes to 0, I get dy over y, 1 minus y. And notice that that's exactly what we saw was the canonical form for this interval. So when I go to this, in other words, the form lives everywhere. The form lives everywhere in this whole space. Omega is defined everywhere. But when I take the residue on this boundary, it forgets about everything else. It just gives me the canonical form on the one lower dimensional positive geometry, which is just that interval. And we can check that that happens in all the other examples too, for both this one and that one. Okay, so that shows you that there's more here than just checking where the poles are. You have to check that as you take all the residues down to all the lower facets, that what you always get is the canonical form on that lower facet. Okay? Now, that's easy to arrange for triangles, for tetrahedra in 3 dimensions, simplices in general. But already there's something interesting in 2 dimensions if we move on to a quadrilateral. Okay, so let's say we have this, let me draw it like this. Oops. All right, so let's say we have this quadrilateral. I don't know why I'm drawing it so bad. Sorry, guys. You'll see why I'm trying to make sure there's no parallel sides, and I'm failing constantly here. Here's a generic quadrilateral. And let's say that the equations that cut out the sides are just some linear equations. I'm not going to write, but there's some linear equation. You know, this is 1, 2, 3, 4. The vertices, there's some linear equation. L1 goes to 0. L2 goes to 0. Maybe I should call this L1 goes to 0. L2 goes to 0, L3 goes to 0, L4 goes to 0. Okay, so there's just some linear equations that define these all these boundaries. Okay, now what do we think the canonical form is now? Well, it should still be dx dy divided by L1, L2, L3, L4. Clearly, we have to have all those poles because it needs to have singularities when we hit any one of the edges. But this is not good enough. The reason it's not good enough is, let's see what happens as, let's say, I take a residue as when L1 goes to 0. Okay, now what happens as L1 goes to 0? Drawing it again like this. I don't know why I'm doing this so badly today, even more badly than normal. Okay, so okay. So let's say here's L1, L2, L3, L4. Now here's the problem, that the form was dx dy over L1, L2, L3, L4. Let's say I send L1 to 0. That means that I'm restricting myself here. Okay, now where on this line can I have other singularities? Okay. I can have a singularity when L4 goes to 0, right? Well, the singularity where L1 is 0 and L4 is 0 is just that point. That's fine. That's part of the geometry. Similarly, I can have another singularity where L2 goes to 0, and that's also fine. That's this point. But the problem is that nothing stops me from also having a singularity where L3 goes to 0, and that's this bad point out here. Okay, so this is where L1 and L3 goes to 0, and this is not in the positive geometry, not in the geometry. So if I don't do anything else, I will not have this form only has singularities on the boundaries and only on the boundaries of this quadrilateral. Similarly, I have a problem over here. Here's another problem point. So I have these two problem points where if I don't do anything more, the form can also have singularities there. I don't want it to have singularities there. So what is the solution? The solution is that there has to be an interesting numerator to this form. Okay, so if we go back, I have to have L1, L2, L3, L4 with some numerator. And that numerator needs to have the property that has the zeros on these two bad points, where L1 intersects L3 and where L2 intersects L4. Okay, so these were my two bad points. So this is where L1 intersected L4. This was where L2 intersected L4, where L1 intersected L3. Right? So in other words, n has got to be that linear function that is just a line that passes through these 2 points. So you see that finding, in this case, finding a canonical form was a little interesting. We have to have the poles in the right spot, but we also have to have a fancy numerator in order to make sure that it only has singularities on the geometry, even going down to lower codimension. This gets more fun if we talk about Pentagon. So let me draw this pentagon, and I'm drawing it this way. So imagine this is the geometry we want. Okay, so now there would be 5 lines, L1, L2, L3, L4, L5. And now there are 5 bad points that we could have. There are 5 places where pairs of numerators, so omega would be dx dy over the 5 lines. But that's not good enough because we have to go to 0 on every one of these 5 bad points. And fortunately, there's a unique conic that passes through all 5 points. And so you put this conic upstairs, this quadratic function of x and y upstairs that passes through all the points, and that's the right answer. Right? So you see that already, even in these really simple cases, like the canonical form for these 2-dimensional polygons, it's interesting. It's not trivial. But there is a form that's a slave to the geometry that has the property that has singularities on and only on the boundaries of the geometry. Okay. Now, what I just showed you in these examples is essentially using the definition of the positive geometry on the canonical form to determine what the canonical form is. In other words, directly find the form with logarithmic singularities on the boundary and only on the boundary of the geometry. Doing it that way gets increasingly complicated for more interesting examples. And so we have to find sort of strategies for determining canonical forms. So strategies for finding canonical forms. So one strategy is that we know, so strategy number one, you can call triangulation. We know, for example, we saw that we know the canonical form for a triangle. So this is easy. Also for simplices in general dimensions. But let's say I want to find the canonical form for this quadrilateral that we just did a second ago. Well, there's a kind of obvious thought, which is, what if I triangulate the quadrilateral? Can you guys see? What happened here?
Yeah, we can see.
We can see, okay. Okay, but somehow
we lost your video though, but that's okay, I guess.
Okay, I think just a moment. I think. Okay, well let me keep going with this. We'll see if we can bring this back to life. Very strange. All right, I'll try to get back on the other side, but let's keep going here. Okay, so one idea is, so let's say we have this 1, 2, 3, 4, is that the canonical form for this whole quadrilateral is actually the canonical form for the triangle 1, 2, 3, plus the canonical form for the triangle 1, 3, 4. Now, why is that? Well, obviously the canonical form for triangle 1, 2, 3 has singularities here, there, and it also has logarithmic singularity there. That's not a singularity of the whole geometry, obviously. 1, 3, 4 also has a singularity there, and also, of course, the ones that we want on the other side. Now, here's the key point. The key point is that when I take a residue of, let's say, omega 1, 2, 3 on the line 1, 3, so in other words, if I take a residue of this form when 1, 3 goes to 0, when it gets there, that residue completely forgets about where it came from. I mean, it's just the form of logarithmic singularities on this interval 1, 3. So in other words, that residue is exactly the same on 1, 3, whether you take the residue from this triangle 1, 2, 3, or whether you take the residue from this other triangle 1, 3, 4. And that means that, at least if the signs are correct, when you add the forms, there is no residue at all on the inside, and instead you just get a residue, the correct residues with the singularities where they should be, just on the outside. Okay? So that's the basic idea. You can prove that it works in general. It's kind of it's not quite as trivial as you might think. It's pretty trivial. So one strategy. So that's a strategy of triangulation, and this is one of the most common strategies in this business. For example, you can triangulate like this. You can triangulate like that. And one of the sort of general points when we get to more interesting examples is that there are kind of classes of triangulations, and different classes of triangulations are associated with making different features of the answer manifest. So there is no God-given triangulation. and lots of different ways of breaking the object up into elementary triangles is making different features of the physics of the amplitudes objects. Let me mention one simple and nice fact, which is that you can either so if we have a let's say we have a polygon. So this has vertices V1, V2, V3, and there's edges E1, E2, E3, and so on. So if this is a polygon, we also have a notion of the dual of the polygon, and the dual is the picture where all the edges are vertices and all the vertices are edges. So here, now we just have, in this case, it's very simple because duals of polygons are just other polygons, but this is a picture where now these guys are edges and these guys are vertices. And a quite simple and nice fact is that the triangulation of P dual also gives a triangulation of P. So let me illustrate this. So let's say I go back to my quadrilateral. Okay, well, one triangulation I can have here is like this one, the one that we talked about. All right. Now, let me draw the dual of the quadrilateral. Also looks like a quadrilateral. So this is 1, 2, 3, 4. All right. And I'm going to do a sort of a, so this is P dual. So I'm going to do a sort of another kind of obvious triangulation here. I'm going to put some sort of point star inside, and I'm going to look at these triangles. Okay. Now, what does that look like back in terms of P? So I've triangulated P dual. What does this look like back in terms of P? Well, in terms of P, what I have, here's P again. This point that I had inside, this point here that I have inside in the dual space, now it becomes a line outside the space. And this triangulation that I had, where every triangle involved this point and an edge, that here, each one of these edges is now one of the vertices in this picture. Okay. So let's say I take this one. So this triangle, I don't know, let's say this triangle here is now going to be a triangle that has to do with this vertex and this line. So that's obviously this triangle. And so you see that there's a funny way of triangulating this quadrilateral just by just using its vertices. So I go to every vertex. So let me draw it. Let me draw it again. Maybe I'll draw it like this, so I make it slightly less parallel lines again. So let's say this is star. I go to every vertex and I just draw the triangles extending the sides meeting at the vertex. Okay, so there is one. Here's another one. Here's another one. And so you see that I can give a triangulation of the quadrilateral made up out of triangles associated with each one of the vertices. I go to each vertex, I look at the edges ending at that vertex, I extend them out to this special line, and this gives me the sort of inclusion-exclusion type triangulation of the whole of the quadrilateral. This quadrilateral is this big triangle minus this triangle minus that triangle plus this little triangle. Okay, so that's interesting, and in fact, there's a class of polytopes for which this always works. It always works in 2 dimensions. There's a class of polytopes that are known as simple. And simple means that at every vertex V, you have, it looks like locally like a simplex. In other words, at any vertex V, the number of facets meeting on that vertex, the number of facets meeting at V is equal to, if it's an n-dimensional polytope, the number of facets is equal to n. Okay, so all polygons are simple, but a tetrahedron is simple. But for example, a square pyramid is not simple. Okay, a square pyramid is not simple because in the neighborhood of that corner, there are 4 facets meeting, and 4 is bigger than 3. It's a 3-dimensional polytope. Okay. Okay. So for any simple polytope, this idea of the triangulation of the dual gives me a formula for the canonical form, which is the sum of the vertices and then the d log of all the linear factors associated with the faces meeting at that vertex. And in fact, there's a sign, and the sign is easy to work out. It's just given by the sign of the determinant of the Jacobian of all those dLi by dxj. Okay. So this is at least one class of triangulations. There are many others, but it's one class of triangulations, and I'm talking about them because they will end up being the origin of Feynman diagrams when we talk about when we go back to kinematic space and we talk about the biadjoint theory. Okay, so that's one strategy. Here's another strategy, strategy 2. Strategy 2 is to look at something, it's to start with a really simple positive geometries. Like, let's say we just have this upper quadrant. So let's say x1, x2, and here the canonical form here is dx1 over x1, dx2 over x2. And in fact, it has a singularity at infinity. So this is slightly more invariantly, if you think projectively, this is really the inside of a triangle. But in any case, this is the sort of most obvious d-log form that has logarithmic singularities on the boundary of this space. Now, okay, great. So that's the form here, and the question is, what can we? So this is such a simple form. Since we know the form for the, one thing we've already done, we know that if we know the form for a simplex, we can just add them up together to get the forms for more complicated shapes, right? But we want to do something else. We want to see, is it possible, can we map? Is it possible to map? Can we find a mapping, actually a one-to-one mapping between, let's say, this guy and our and the geometry that we're interested in. Okay. So really, what we want is we want to see, is there a mapping between just this positive orthant, this positive quadrant, for example, to the inside of a general n-gon, which is one-to-one. At least, in other words, when x1, x2 is inside here, it uniquely maps to some point inside here, I don't know, capital X of x1 and x2 inside the n-gon. Now, let's say we can find such a transformation. We'll talk about what those transformations look like in a second. But then there's really there's a beautiful fact, which is that if you take the sort of simple form like dx1, dx2, the one here, then you can push this forward with phi to get the canonical form for the geometry that you map into. What this means literally is that the mapping is giving me some point x, which is a function of the little x's, right? Again, this is the map from the simplex into the positive geometry. So this is some x that depend on the x's. The claim is that it's that it's one-to-one in here, in the sense that any point in the quadrant is sent to uniquely to a point in the geometry. And then all you do is you take the form dx1 over x1, dx2 over x2, in any number of dimensions, dxn over xn, and you just evaluate it on x of x equals whatever x you want inside here. So it's going to give you a form on the image. Now, what do we mean when we say evaluate? I told you that the map is one-to-one in the reals here. In other words, it's one-to-one from the interior of this sort of positive region here to the interior of the positive region on the right-hand side. But the equations that we'll end up doing this are quite nonlinear, and so in fact, a given point x here will have many pre-images. We'll have many x's, x1, x2, there will be many solutions. The claim is that there's a unique one here, there's a unique one which is real and positive, okay? But it has many other solutions. But the claim is that if I simply sum over all the solutions of x equals the x that I want, of d log little x1 up to d log little xn, I get the canonical form for the geometry in X. Okay, so that's the second strategy. Okay, so this is the push forward strategy. In order to make this strategy useful, you need to find some way of actually doing this mapping. And there's a very pretty way of doing this mapping when you have polytopes. So again, let me illustrate with a case of a polygon. So let's say we have this polygon, and let's say the vertices of the polygon are 1 through n. Then of course, any point inside the polygon, any point inside can be written as some positive weight 1 times vertex 1, positive weight 2, vertex 2, some weighted positive sum of all the vertices. But this is a highly redundant map, right? If I give you, for example, this space is the polygon is two-dimensional, but I have this highly redundant map with like n variables here, okay? So what I want is some way of parametrizing these w's in this two-dimensional example in terms of two variables, x1 and x2, such that I get a one-to-one map from the little x1, little x2, both greater than or equal to 0, into the polygon. And here's the beautiful way that it happens. So the Newton Polytope map, just the name. Here's what you do. Let's say you have your favorite pentagon. So you have some particular pentagon you have in mind, and you want to find a way to map into the pentagon. You want to find a map from the inside of this quadrant into the pentagon. Well, here's what you do. You first just draw an integer representative of your pentagon. So here's a grid. You just draw a pentagon, but with integer coordinates, any one you like. So here's one. So this would have coordinates 0, 0, 1, 0, 2, 1, 1, 2, and 0, 1. Then the claim is that there's a lovely formula for the weight of any, for the weight here that we're talking about for any vertex. Let me remind you that we're trying to write x is equal to some weight 1 v1 plus, in this case, weight 5 v5 divided by weight 1 plus up to weight 5. And the formula is just that the weight for vertex 1, so this would be vertex 1. The weight for vertex 1 is x1 to the power of 0, x2 to the power of 0. The powers are just given by the integer coordinates. This would be vertex 2. So the weight for vertex 2 would be x1 to the power of 1, x2 to the power of 0. The weight for vertex 3, this is vertex 3, would be x1 to the 2, x2 to the 1. For x4 would be x1 to the 1, x2 to the 2, and for 5 would be x1 to the 0, x2 to the 1. And the amazing thing is that this has the property of mapping. This has the property that is exactly the property that we want. It maps uniquely all the points in this upper plane to the interior of the polygon, right? So, so remember, this map we'll be seeing it in action. Well, if we get there, we'll be seeing it in action a little bit later. Okay, so this is the second strategy, is a push forward. This is really cool, and I encourage you to play with it. The sort of interesting thing is that as the little x's go off to infinity, what's going on is that the little x's go off to infinity in different directions. Different terms in these, as you go off to infinity in different directions in little x space. So if you think here is little x space, as you go off to infinity in different directions in little x space, different ones of these monomials will dominate. And so each one of these directions actually ends up getting mapped to one of the vertices of the polygon. Well, in this case, it was a pentagon. Okay, so different monomials here dominate, and so in different directions, you end up getting sucked into different vertices. But then at the boundaries of the directions, you end up getting you end up hitting the edges between the vertices and so on. So, okay, so this is something that you can even play with in Mathematica to see that it's true. But the claim is that this gives you a one-to-one map from the inside of the from the upper quadrant or the upper quadrant in general for general dimension polytopes to the interior of any polytope. All you have to do is take an integer representative of the polytope and do the push forward. Okay, the final strategy, and this is one I'll now explain a little bit, is the idea, and this is a newer one, is the idea of stringy canonical forms. Actually, there's a number of other lovely ways of giving an invariant description of the canonical form of polytopes. They're often associated with, you can think about them as associated with the volume of the dual of the polytope, and there's a few others. But they won't be relevant. Those won't be relevant for the rest of the story. So let me finally tell you about stringy canonical forms. And here, by going back to a very simple form, like dx1 over x1, dx2 over x2. Now, beforehand, we said, why can't we sort of map this somewhere? We can push it forward somewhere. Well, now we're going to ask a simpler question. Here's a form. It's associated with this region, right? x1 and x2 positive. So why don't we just integrate the form in the region? Why don't we integrate this form over the region where it's defined? I mean, that seems like a natural thing to do. And well, why don't we do that? We don't do it because the answer is infinity. Okay? We don't do it precisely because the answer is logarithmic singularities on the boundaries of the, as x1 goes to 0 and as x2 goes to 0. Okay? But that suggests an interesting thing that we can try and do instead. So we're going to do the following thing. So and these are the stringy canonical forms. So let's say we have a form that looks like dx1 over x1 up to dxn over xn. And I want to integrate it from 0 to infinity for everyone. Obviously, it's divergent. But what we're going to do is sort of regulate that divergence in an obvious way. And this is an ancient idea. It goes back to Euler. Many people have studied aspects of these integrals before. The integrals are not new. The association with them with a form is somewhat interesting, and is the newer part. So I'm going to regulate it by saying I'm going to regulate these divergences as little x goes to 0 by putting a power here, and I'm going to put a coefficient alpha prime. And if you're a string theorist, it looks like a string scale, but and that's where the stringy terminology comes from. But you can just also think of it as just some epsilon, some small parameter. Okay, so alpha prime x2 and so on. So xn to the alpha prime xn. Good. I have now saved the divergence as x goes to 0. If alpha prime and the x's are positive, then this has regulated the divergence near x goes to 0. In fact, as x goes to 0, I would get out of this something that goes like 1 over alpha prime to the power of n. So in order to just normalize that, I'm going to put an alpha prime to the n in front of the whole thing. Okay? But the problem is I'm still not done, because this integral still diverges as the little x's go to infinity. Okay? So in order to deal with that, I'm going to just put, for the moment here, just some polynomial p of x to a negative power. All right, now this has a chance of converging. Okay, this integral has a chance of convergence. Let me call this integral I. It's not a form yet; it's just an integral. Let's look at the sort of simplest example. The simplest example would be just a one-dimensional positive geometry. Would have integral 0 to infinity dx over x. We haven't. And now I'm going to put some x to the alpha prime. Let me just call this a. And now, in order to regulate the behavior at infinity, I can put, for example, 1 plus x to the minus alpha prime. Let me call this c. Okay, that's the simplest example. Now, without, of course, many of you will immediately recognize this as the formula for the beta function, for Euler's beta function, or the Veneziano amplitude in string theory. But without using that knowledge, let's just see, what does it take for this integral to be convergent? What does it take to be convergent? Well, obviously we need to have a as positive, but also a can't be too big, because what's saving the behavior is a little x goes to infinity is this power, and if that's overwhelmed by a, then the integral won't converge anymore. So I also have to have that a is less than c, so greater than or equal to 0 and less than or equal to c. Okay, so in other words, if I just draw, so here's this sort of interval from 0 to c, a has got to live in here. Okay, okay, good. Now, what is this actual integral? The actual integral is gamma of alpha prime a, gamma of alpha prime c minus a, it's the beta function, over gamma of alpha prime c. And indeed, as alpha prime goes to 0, the integral is equal to c over a minus c, or 1 over a, c minus a, or 1 over a minus 1 over a minus c. Okay, so as expected, since it only converged when a was bigger than 0 and a is less than or equal to c, it's not surprising that it has a pole as a goes to 0 and a pole as a goes to c. Okay, and so that's our simplest example of this integral. But now we're going to do a little bit more than the integral. We're going to think about a form in general. I'll say what the general story is, and then we'll specialize that example. The form is dx1, is a form in the space of those exponents. So, sorry, there's an alpha prime to the n in front of the whole thing. Then I have dx1 over x1, dxn over xn, x1 to the alpha prime capital X1, little xn to the alpha prime capital Xn, and then this general polynomial, p of x to the minus alpha prime c. Okay. Now, let me now make some claims, and I hope the claims will be plausible, and we'll see them from the example. So first of all, in our example, this form would just be, let's say, dA, 1 over a minus 1 over a minus c. And you'll notice that this is exactly the canonical form for this interval, right? So this is just the, we had this interval, a was between 0 and c. So this is just exactly the canonical form for this interval. Okay, so putting the dA here made it into a differential form with logarithmic singularities on the boundary of the space. Trivial in this case because it's just one-dimensional. Okay, but here are the claims. So here are the claims. So claim number one is when is the integral is convergent, and when, if I group all these exponents, these x's together into a big vector x, when x lies inside a certain polytope. And that polytope is given by that constant, and it's called the Newton polytope of the polynomial. So let me explain what this terminology means. So what is the Newton polytope of a polynomial? So let me give an example. Let's say I have a polynomial, I don't know, 1 plus x squared y plus x cubed plus x to the 5th, y to the 5th. Okay? The Newton polytope is just, I plonk down a vertex. I look at all the monomials. So this is x to the 0, y to the 0. I look at all the monomials. The coefficients here don't matter. Okay? I just look at the monomials, and every monomial gives me what you can call an exponent vector. So in this case, it would just be 0, 0. And then I just draw it. Here is 0, 0. Here there would be, that's like, here there's one that's 2, 1. Here there's one that would be 3, 0 out here. And here there's another one which is out here is like 5, 5, right? Okay, so I just take all those monomials, and the Newton polytope is just the convex hull of all those monomials. So in other words, I just imagine I take all those points and I just look at all the positive combination of all those vertices that I could get. It's known as the convex hull of all the points. Okay, so that's the Newton polytope of a polynomial. Okay, so the Newton polytope of a polynomial is the convex hull of all the exponent vectors of the polynomial. And intuitively, what's important about the Newton polytope is that the vertices of the Newton polytope tell you that in different directions, as you go off in xy space and you scale x and y to infinity in different ways, different ones of every vertex will have a chance to dominate somewhere. In some region in xy space, some vertex will dominate over all the others. If it so happens that some of the monomials are inside, like this example, then that vertex never dominates. In every direction, there's someone else who's dominating. So that's what's sort of important about the Newton polytope. It captures and it tells you, as you go off to infinity, who is going to be dominant and who dominates over who. And you see, for our purposes, I mean, that's one of the things that's important about it. For our purposes, that's what matters, because we're interested in figuring out when this integral converges. So we have this integral, dx1 over x1. We have this, we've saved things down at infinity. We've saved things down at 0 by putting these factors. But we have this polynomial, p of x to the minus alpha prime c. And we want to know when this is going to save the integral at infinity. So obviously we need to keep track of which terms are dominating as we go to infinity. And therefore it's reasonable that what matters for the convergence of this integral is just the Newton polytope of p. But the lovely thing is that if I make a form out of this, so again, alpha prime to the n, same integral that we just talked about. Oops, capital X1, capital Xn, p of x to the minus alpha prime c. So the claim, let me finish the claim, is that this is convergent when the x are inside c times the Newton polytope of p. And 2, as alpha prime goes to 0, omega goes to the canonical form of exactly that polytope. Okay? And that's what we saw in our simple one-dimensional example. So in other words, the stringy canonical form, now it turns out to have lots of nice properties even at finite alpha prime. But the stringy canonical form, for our purposes at the moment, is a way to build a canonical form, which naturally comes along with an alpha prime, but you can send alpha prime to 0, can give me the omega canonical for any polytope that can be represented as the Newton polytope of some polynomial. Which is almost everything that we might care about. Actually, amusingly, not everything, but almost everything that we'll certainly care about in physics. Okay, so this is a third way of determining a canonical form that naturally comes along with an alpha prime. And let me make a final comment about this, and then we'll take another break. The final comment I want to make about this is what happens if there are many polynomials and not just one? Well, before telling you that, let me tell you a very simple fact. Let's say you have one polynomial. So let's say we have polynomials P1 and P2. Well, it's natural to ask about the Newton polytope of the product of the two polynomials, P1 and P2. And if you just think about it for a second, this is sort of obvious what this is. This is, after all the monomials you get in P1 and P2 are the monomials you get in P1 plus the monomials you get in P2. And so that means that everything you would get in the convex hull is just any vector you get in the convex hull of P1 plus any vector you get in the convex hull of P2. And that notion is formalized in something known as the Minkowski sum. In other words, the Newton polytope of P1 times P2 of that product of polynomials is the sum of two polytopes. But the sum is this notion of Minkowski sum, Newton polytope of P1 plus Newton polytope of P2, where the notion of A plus B is just the set of all V plus W, where V is in A and W is in B. Okay, so really simple idea. This is known as the Minkowski sum. Okay, so that's kind of an obvious fact and an obvious feature of obvious property of Newton polynomials and Newton polytopes. And so that lets us immediately answer the question what we get if we have a more general integral of this form, dx1 over x1 up to dxn over xn. Again, we have our, Again, we have our alpha prime to the n and all the dx's out in front to turn into a form, but that doesn't matter for this. Let's say we now have p1 to the minus alpha prime c1 up to pj to the minus alpha prime cj. Then the answer is that this is equal to the canonical form. So it converges when x is inside C1, P1, Minkowski sum, C2, P2, Minkowski sum, all the way, Minkowski sum, CJ, PJ. The reason that that's obvious is that imagine for a moment that these C's were rational numbers. Then you can think of this big product, P1 through Pj, to the minus alpha prime C1 to J, is secretly an enormous polynomial to a fractional power. And so we can just go back to our previous analysis, where what we have is the Newton polytope of that giant product of polynomials to powers. But the Newton polytope of that giant product is simply the sum, the Minkowski sum of all the pieces. So that's why this statement is actually natural and obvious. And it converges then, and omega, as alpha prime goes to 0, goes to the canonical form of exactly the same polytope, C1, P1 plus C2, P2 plus CJ, PJ. So I mentioned this, so we see that when some polytope is naturally presented as a Minkowski sum, and we'll see this in a bit, when some polytope is naturally presented as a Minkowski sum, we have a natural, the stringy canonical form is a natural way to compute its canonical form. Okay, now there are a lot more things we could say about stringy canonical forms. They're related to scattering equations and other things like that, but I think that's all I will need for my purposes. So let's just stop there. Are there any questions? Okay, should I, sorry, because my other machine died for that period, I'll try to get it back up in this little break. But that's why I couldn't get to the questions as we were going, because I couldn't actually see them. But are there any questions that you'd like me to answer now before we move on?
And Nima, I have a simple question. Does it matter if one of the coefficient CRs is irrational or transcendental or something?
No, it doesn't matter. But that business about assuming they're rational was just to give a quick argument for why the answer that we got was the answer. But they don't have to be. Yeah, they can be any real numbers.
Thanks.
Okay. Should we take another 5-minute break?
Sounds good.
Okay. All right, see you guys in a bit. Meanwhile, I'll try to get my other thing going here.